Last time we derived the expression for torque on a current loop because of a uniform magnetic field. If you have current going in a closed loop, some current I going in a closed loop, and you have uniform magnetic field, the field cannot exert any net force on this loop, but it can exert a torque on this current loop. And we derived the expression for that, and that was, if you have this current loop, let us say this is current I, then uniform magnetic field B, then we wrote torque is equal to I, this I, let me write capital I. So, the current and times area vector A, and then cross product with B. What was area vector? Area vector is, if it is a plane loop for example, then you take perpendicular in the direction perpendicular to the plane of the loop, and the magnitude of this area vector is actual area of this in whatever units, length square, and the direction of A, it is perpendicular to this loop, that is okay, but which perpendicular? There are two sides. For that, this arrow is important, the direction of current is important. If you look into the loop and you find that the current is anti-clockwise, then the area vector is towards you, and if you find that the current is clockwise, then the area vector is going away from you. So, that is the convention, and that is how you write this A, and then I A cross B is the torque because of the magnetic field, because of the force that this magnetic field exerts on each of the current element, the net current, the net force is 0, but then it is exerting force on this part, it is exerting force on this part, this part, this part, this part, and so on. The net is 0, but all these individual forces, they have torques, and these torques add to give you this I A cross B. Okay. Now, this I A, this quantity is known as magnetic dipole moment. Magnetic dipole moment of the current loop. Remember electric dipole moment, if you have some charge distribution, then we define electric dipole moment, and the definition is there. We had done it in our electrostatics course, but essentially a very simple dipole can be thought of if you have two charges plus q and minus q close by. And what is close by? This separation between these two is small as compared to the distances of interest. If I am interested, what is the field here, or what is the field here, or what is the field here, compared to those distances, this should be small. This we call electric dipole, and then we define electric dipole moments, which is q times this separation d for this particular configuration, and the direction is from negative charge to positive charge this way. And then if you have an electric field, uniform electric field, then there is a torque, and that torque is this dipole moment cross E, and that we can derive very easily. The force on this plus q is q times capital E, force on this minus q is minus q times capital E, and then we can write the torques and add and see that the torque comes out to be this. Now, it is a similar expression, if you write this I A as some dipole moment as it is here, we give it a name mu cross B. So, this mu is playing the same role. Torque is mu cross B, torque is P cross E. So, like this is called electric dipole moment, this is called magnetic dipole moment. So, magnetic dipole moment of a current loop is essentially the current multiplied by this area vector. So, that is how we get this. So, this is one justification why we are calling it magnetic dipole moment, although we do not have two poles. Just like here you have two charges minus q plus q, or a charge distribution which can give you similar kind of impact. But then here we do not have any such two poles or two charges or 2 points, but still we call it magnetic dipole moment because of the similarity of the torques, and also we will see that similarity of the field produced by this current loop, that we will be later. So, this is one thing that you have to keep in mind. Now, this was for a current loop, but the current can be in different fashions. This is a linear current, right? This is a linear current. We can have surface current. We can have some surface where you have surface current, and because of that surface current you have all kinds of things. If there is a uniform magnetic field, it can exert torque on this surface current, or you can have volume current. On that volume current also, if it is a closed volume, and then you have currents there, and there is a uniform magnetic field that can exert a torque on that. So, we generalize this IA expression is only for a linear current loop. This is for a linear current loop, but we can generalize it for surface currents and volume currents also. So, let us first write it in a slightly different manner. This magnetic moment mu of this current loop is I times area vector. This is the current situation, but this area vector can be written in a slightly different form. Suppose you have origin somewhere here in this plane of this current loop, and then let us see, if you connect this origin to certain point here, and then some dl distance here, and then you connect it here. So, this is, let us say, r vector, and this is dl vector. Now, this is a triangle kind of structure. This is a triangle kind of structure, and we would like to know what is the area of this triangle like structure. So, to get that area, if you have let me draw it here slightly bigger. This is our dl, this is the vector r, and let us say the angle between this position vector and this dl here is theta, let us say this is theta. Now, to get the area of this, what you do? This is the base, and then for height you extend it, drop a perpendicular, draw a perpendicular and get the height. Okay. To get the area of this triangle, what will you do? Take this as a base and then see what is the height of this triangle, and for height you extend this and draw perpendicular from here. So, this height, how much is this height? If this length is r and here is the angle theta, this is 180 minus theta. So, r sin theta, right, r sin theta. Sine of this angle is same as sine of this angle, right. Sine of theta and sine of 180 minus theta, they are same, and therefore you have r sin theta. So, r and then sine theta of this, which is h by r. So, that will give you the height, and therefore, the area, this area dA will be equal to half into height into base, and that base is dl. The base is dl, this base is dl, and this height is r sin theta. So, half into base into height, that is this area of this triangle. Now, this you can write as half, and then this is r vector cross dl vector. Check. That is the definition. The magnitude of r vector cross dl vector is magnitude of r, magnitude of dl into sine of the angle between these two. So, that is this angle theta here. So, this is dA. Now, you can see that if you take this area and write area vector corresponding to this is in the same plane. So, the perpendicular will be the same, and therefore, you take this area dl here, or you take the dl here, or you take the dl here, you take the dl here, anywhere you take that dl, all the time that area vector is same. So, you can add to get that total area vector, you can add this plus this plus this plus this plus this plus this and so on. So, this area vector here is will be just integration of this r cross dl, half of this integration of r cross dl. The magnitude of this whole thing, you first take the magnitude and then integrate, or you first integrate and then take the magnitude. It's same, because all these elementary area vectors are in the same direction. So, they just add up arithmetically. So, this is your A vector. A vector you can write it like this, and therefore, this expression becomes now torque is equal to I into area vector A. Area vector is half, and then integration of r cross dl, this is it, and then cross B. So, it is cross B. Remember, B is a constant vector, right? B is a constant vector. Now, this you can write as half integration, so r vector and cross ideal, take this r vector inside this and then cross B. This is the torque, and mu, in fact, I was interested in mu, not in torque. Mu is just IA, this is mu. So, mu is I times A, that means I times area, and area is half here, and integration r cross dl here, and this is equal to half here, and then r cross and I dl. You can write this expression mu is equal to IA in this fashion, and this removes the simplifying restriction that we had taken, that loop is in one single plane. Even if loop is not in one single plane, then also you can all the time write r cross dl, right? Whatever is the shape of this loop, it goes horizontally, then it rises and then come back. Everywhere you can get the dl, and then you can calculate this and get this mu. And not only that, you can have different shapes of the current loop. This expression can be generalized for other kinds of currents like surface current and volume current. Remember, we had current elements, we talked about current elements, and if it is a linear current, then we said that okay, this will be our elementary current element. If it is surface current, then it will be K and then dA. dA is area. If you have a surface on which there is a surface current, then that k is defined by taking a line on that surface and then looking how much charge is going from one side of the line to the other side per unit time, and that is how that k is defined. And then the area that you are taking, that will be multiplied with this, and k dA will be the current element there. This will be the current element there. And if it is a volume current, like a cylindrical wire, so if it is a volume current, then the current element will be just J, current density. You have a volume and then you take a surface area, some cross sectional area, and then see how much charge is going from this side to that side per unit time, and from there you define this J, the current per unit area, and this into d tau. Take a volume there. So, if it is a volume current, take a volume there, see how much is the current density J, and then J times that volume is the current element. If it is a surface current, then on the surface you take some dA, and at that point see how much is k, k dA is the current element. If it is a linear current, then you take this dl, and then I dl is the current element. So, this substitution often generalizes your expressions. If you get the expression for a linear current, then this substitution you can use to generalize it for surface currents and volume currents. So, this mu for a surface current will be half integration r cross ideal is now replaced by kdA. Remember, these are all closed currents, right? It is all closed current. There is a closed surface on which the current is going. There is a volume, closed volume in which all those current elements are there. It is a loop, so a closed loop. So, remember that you can put this circle out here. So, this will be for surface current, and mu is equal to half, then integration r cross j d tau, j t tau. This will be for volume current. So, this is for surface current. This is for volume current, and this is for linear current. So, these are the generalized expressions for magnetic moment. These are all magnetic moment expressions. Now, another thing I would like to do today is a relation between angular momentum and magnetic dipole moment. Now, suppose you have a material, and that material has mobile charges which can move and create currents, and the mass density let me write as d at r at a certain, you have a material here, and then this is a position, and here I make some d tau, some small volume, and ask how much is the mass of this divided by the volume, that is mass density, and that is, let us say, it is d. And then you also have charge density. And this is the charge corresponding to the ones which can move on applying electric field and can create current. So, that charge density is, let us say, rho at r, and let us say that d is equal to some constant times rho. What does this mean? This means wherever you have mass, you have charges which can move or which are moving, and then the charge density there and mass density there, they are proportional. So, the entire material has that mobile charges, and if you take a bigger volume, the mass will also increase, the charge will also increase, and therefore this kind of relation can exist. Now the task is that if these charges move and create a current, then it's in a closed volume, and when I say closed volume, it can be closed surface, it can be closed loop. So it is a closed volume in which the charges are moving, and therefore it will have some magnetic dipole moment. At the same time, you have mass which is moving. If mass is moving, then it will have some angular momentum. So our task is to write expression for angular momentum and magnetic moment and see if there is some relation. Okay. So we can start with any one of them. Let us write angular momentum first. So if this is dm, if this mass is dm, and then it is moving with some velocity v, and here is the origin, so the definition of angular momentum is r cross p vector, and p vector is now the linear momentum vector. Remember, L is equal to r cross p. This is the basic definition for a point at this r. That means angular momentum is also defined about a point which we call origin. So from origin, where is that particle? So that is r vector, and this is your mass times velocity vector, linear momentum. That is how the angular momentum is defined. So if I ask about this small part here dm, right, small part here, the angular momentum will be this is r vector and cross mass is dm and v. So this is the angular momentum of this part, and if I integrate over the entire material, that will be the angular momentum L. On this entire volume we are integrating. So this is angular momentum. And what is magnetic dipole moment? Magnetic dipole moment. We just wrote that mu is equal to half and then r and cross j d tau. We are writing the most general j d tau. If it is a surface current k dA, if it is a linear current I dl. So this is the magnetic moment. This j is current density, right, volume current density, and this is rho times v. Remember this relation we derived, this is rho times v. J is rho times v. This rho is charge density. So if you have charge density and then this is moving with velocity v, that is rho times v will be the current density. So you can write this mu as half integration r cross rho, which is the charge density, and times velocity, and then this d tau, this is mu. Anything common with this and this? Anything common? Here it is r cross half is there, then you have v, here you have dm, here you have rho times d tau. This dm also you can write. Okay, this dm also you can write, because we said mass density is d. So this dm is mass density times the volume. So this you can write as integration r cross dm. Dm is the D, remember this D, don't get confused, D times d tau. This is mass density. So density into volume is the mass. So this d density into this volume d tau. This is mass dm. So for dm, this dm I am writing that, and then velocity is v. So it is integration of r cross and then v here, r cross v here, and then d tau. This is L, and mu is here. Mu is equal to, I am just copying, mu is equal to half integration and then r cross v, r cross v, and then rho d tau. So you can see the similarity. You can write from here integration of r cross v. Okay, since we say that d is equal to k times rho, so let me write this as rho, k times rho. So this d is k times rho, right. So from here you can write r cross v, rho d tau is equal to L divided by k. Let us see if I have written it correctly. This L and divided by k, what is left? R cross v, rho d tau. So this is L by k, and from here this same thing, r cross v rho d tau, integration, that is 2 times mu. This is 2 times mu. All right. So that means these are same expressions. So that means L by k is equal to mu twice of mu. All right. So they are proportional. L is mu is equal to, you can take this 2 here, L and divided by 2 times k. And what was k? K is the proportionality constant between this d and this rho. If you want to write how much is the total charge q in that material, the charge which is movable, remember you can have those nuclei and ions fixed at their own positions. We are only talking of the charges which can move, and we have assumed that wherever you have mass, in proportion you have that movable charge there, and that proportionality is given by this k. This is the mass density and this is that movable charge density. So this total charge which is here, that will be rho d tau integrated over the entire volume, and this rho, okay, and what is the total mass? Total mass will be d tau. This is the mass density, this is charge density, this is mass density times volume will give you mass of that d tau, and then you integrate, you get that total mass. And this d is k times rho, this d is k times rho, and k is constant. So this is k and then rho d tau. So if you divide, you get q by m is equal to, q by m is equal to 1 by k. 1 by k is q by m, and here is 1 by k. So this you can write as, this proportionality constant is mu, you can write mu is equal to gamma times L, where gamma is 1 by 2k, and that 1 by 2k is 1 by 2 here, and 1 by k is q by m. So you put q here and m here, so q here and m here. So gamma is q divided by 2m. So, that is the proportionality constant. The magnetic moment, magnetic dipole moment is often in short called magnetic moment. So, if at some stage I say magnetic moment, it is to mean magnetic dipole moment. So, this magnetic moment and the angular momentum, they are proportional to each other, provided you have charge density, you have mass density, and they are proportional. So, this is this. Now, this ratio of magnetic moment and this L angular momentum, that is known as gyromagnetic ratio. So, this gamma is known as gyromagnetic ratio. Very important in atomic physics, when we try to understand the spin of electron, then this concept is very crucial there, that corresponding to the angular momentum, if it is a charged particle which is moving, then corresponding to the angular momentum, we also have a proportionate magnetic dipole moment. So, that concept is very important when we talk of electrons in an atom. So, we will stop here and do something else next time.